Yeah. Why?
Hello and welcome back to Calculus 3. We are going to continue our exploration of vector-valued functions, and now we're going to do calculus of vector-valued functions. So vector-valued functions, what do? They give us curves and lines in third-dimensional space. So now we can do calculus with those, and calculus consists of limits, derivatives, and integrals. So I can take care of the entire lecture in 3 words and just move to the next section.
Really?
Yeah. That's it. Done. Next section. 11.7 motion in space. This is really what's happening here, guys, for 11.6. You know that your vector valued function r as a function of parameter t, let's say, is given as f of t, g of t, and h of t. So if I am supposed to find the limit of r of t, well, that is going to be the vector where the limit that t goes to some value. So it's just done term-wise, as I said. So you will apply limit to f, and then separately limit to g, and separately limit to h. And you will do the same thing with derivatives and integrals and call it a day. So limit t goes to a of g of t, and limit t goes to a of h of t. Welcome. If you want to call this a formula, you can call it a formula, but it's really not that special. At the same time, the derivative in respect to t of your vector r of t, no coughing, is the derivative of f dt, derivative of g dt, derivative of h dt. You can call this a formula? Sure, you can call it a formula. There you go. It's a formula. It's a formula if you put a box around it, right? And then the integral of the vector valued function dt is going to be again a vector. Integral of f of t dt, integral of g t dt, comma, integral of h of t dt. All right, so I'll let r of t be given as 3t squared minus 1 e to the t and cosine t. Get all three. Compute limit r of t as t goes to 0. Compute the derivative of r of t and integral of r of t. right, sounds like you guys are done. So the limit of the first one is good. How about the derivative? 60?
60.
I know. Every time. All right, so 60. How about our integrals? T minus T plus C. If you don't have plus C, that's -1 on the first coordinate, -1 on the second coordinate, and -1 on the third coordinate for -3. Yeah, so it's 0 for the problem, technically, yeah, on that part. Comma. Keep talking, yep. Plus C, all right, and then? Yes. I know. Great. So, technically this is the way we do calculus on vector valued functions. Each component is going to get its own either limit, derivative, or integral. And now let's talk some concepts here. So if you have your vector valued function R of t given as f of t, g of t, and h of t, we can find its derivative which will be denoted as r prime of t. And now that derivative is going to give us the tangent vector. So this over here is called the tangent vector. And if you have a space curve of some sort, it doesn't matter what the space curve is, you are going to have a tangent vector r prime of t which sits on the tangent line. So all of this is going to sit in a XYZ 3D coordinate space, and there is the r of t vector valued function, right? The r that locates everything, and you can call this, I don't know, point A in space. So what you have here is some kind of a space curve, a curvy space, right? So technically you have this, right? That's what you have. And you are going to have, at each point, you are going to have a tangent line at each point of this curve. There is going to be a tangent line. The slope, the direction of that tangent line is determined by the vector valued derivative, right? Vector that you get from the derivative of the vector valued function. Who can tell me the vector form of the linear line in 3D? What was the vector form? Yes?
It was R of t equals to v times t plus RO.
Excellent. Excellent. So this is a line in any dimension space. This was the last class. Very good, Kevin. So this is the line. You know it as y equal mx plus b for your 2D case. If you want to go 3D, 4D, 7D, this is the vector form of it. Vector r is going to be replaced by x, y, z, and whatever amount dimensions you need. And then r0 is the point through which it goes. And this vector v was that ABC, the direction vector. I called it a slope vector. Right? Well, now, to get the tangent line, it should be common sense. R of t is r prime of t times t plus r0. So we are replacing the good old ABC with this line. Now we are going to compute that at the point that we want, which is going to be point A up there. So all of those play a role here. So let's see. Find the tangent line at I'll leave that because I first have to come up with a function. So let's say vector value function. So for r of t equals 2, and now we come up with some kind of a function over here. So let's do vanilla for now. So t squared minus t plus 1, and I don't know, e to the t. I'm just gonna say at t equals to 2. So find the tangent line for the function r of t at t equals to 2. Clearly you need a slope and a point. You can get the slope using the derivative, and you can get the point by plugging t to calculate the point. So you have everything you need. Just need to put it together. This is your Calculus 1 tangent line problem. Except now you're just grinding through the 3D. Do you have any questions, ask Mike.
Oh, no, make sure everyone knows everyone's name. I thought you were treated as serious and that you were treated like that. Not with one student who didn't match any of the names. Went 2 names apart. And it was him. It was like, yes. And then I had Ryan something. And the only exam I had was Ryan Henry. So a name, first name of one student and last name of the other. It didn't make sense. That was the math. That's all you. Because I think it's when you look at it. Because I had my name like that. Nobody wants to do this already. Nobody wants to do this. Oh, okay. I'm thinking that's what you make. He's trying to make the bed off of you, Andy. You have to ask when I do my third, or my first one. I know you heard. Yeah, no. That's like what the new level. It's too good. I don't want to do the answer. Hopefully. What's the boss saying?
He has no clue what's going on. He's like falling out of one.
What happened last night? Do you have videos for this?
It's hard going.
I like this. It's nice.
Solid.
He's a very nice guy.
Anything before the word but doesn't matter.
I like no, but he is a nice guy.
Exactly. Yeah, that's what you don't focus on.
This right here is
He's the same. I'm not racist.
Perfect. Let me hear it. Let me hear it.
I know. But this lay it out. I want to know.
Okay. So we're going to use t equals to 2 to get the point. And that's going to be 2, 3, and e squared. It's fine. We're going to find the r prime of t, which will allow us to find the slope, which is the, in this case, 2t minus 1, 1, and e to the t. And then to find the vector. So I should have actually said this t computed at time 0 or something, because it has to be a vector, because now we are computing that, so that vector v is actually r prime computed at 2. That's what it is. So our vector v is r prime computed at 2, so that's going to be 3, 1, again e squared. So my equation of the line x, y, z is going to be 3t t e squared t plus 2 plus 3 plus e squared. So that's one form. You can also write it in a form of a vector, 3t plus 2, t plus 3, and e squared t plus e squared. Is everyone happy with this? So to find the tangent line for the vector valued function, you have to find the point. You have to find the vector that gives you the direction of the line, which is that 3D slope with quotation marks. Once you have all of those components, you just put the line together and you are done. Yes. So the formula for the line, the vector formula is R equals VT plus R0, right? So this would be your X, Y, Z, A, B, C, T, T, and T, and then plus X0, Y0, Z0, right? So here are your X, Y, and Z zeros. And here are your ABCs. I just arranged them vertically. So you have your 3,1e squared over here. And you have your 2,3e squared over there. Excellent. Sense the tone. Unit tangent vector. So unit tangent vector is going to be one of the important building blocks of the class. It's going to show up in multiple formulas and things coming up. So make sure you know this like a palm of your hand. Unit tangent vector, which is denoted with a capital T, is going to be r prime of t divided by the magnitude, obviously. We know that to make the unit vector, we just divide vector by its magnitude. So the unit tangent vector is going to be the r prime divided by its magnitude. All right. Find. Now you can also use the hat for it because it's a unit vector, right? You can also use the hat. I'll put the hat over here. You can use arrow, but unit vectors should have hats. So find the unit tangent vector for r of t equals to sine t, cosine t, and t. Actually, let's do the 2D case first. Erase the t. Just do the 2D case first. As you can see, the formula up there doesn't care about the dimension, right? You can have that in 17-dimensional space. You just have 17 coordinates to work with. So let's find first for the 2D. So to find this, we clearly need r prime of t. R prime of t is cosine t, negative sine t, very good. And then we also need the magnitude of that, which is 1, thank you. We square each one of these. When we add them, we get 1. Square root of 1 is 1. So square root of cosine t squared plus negative sine t squared. Well, this is just sine squared plus cosine squared, right? The minus dies because of the square. And you have a square root of 1 is equal to 1. So what is our tangent? Unit tangent vector. Unit tangent vector of t is equal to just cosine t negative sine t, because you are dividing everything by 1. Now, does it make sense? First of all, what is this? What is this? This thing over here, what is this? Very good. What is that when you draw that on xy coordinates? And what kind of curve? What is this? Why semicircle? It's just a circle of radius 1. It's a unit circle. Yeah, this is all the way in pre-calc 2, and then in calc 2, and now in calc 3. Yeah, this should be a massive facepalm over here, like a coordinated one. I go 1, 2, 3, and you go brush. So it's a circle, 2D, right? 2 coordinates, sine, cosine. Now it's not cosine sine, it's sine cosine. That means the orientation is going to be clockwise other than counterclockwise. But it doesn't matter, right? It's still a circle. The number in front of sine and cosine is the same. It's 1. So the radius is 1. What would this be if I put 2 and 3 in front of these guys? Ellipse with radius 2 and 3. Very good. So now we know this is a 2D. If you don't know, this is what you should be writing to know for the future reference. So this is a 2D, right? It's circle, and it's what we have is the vector r prime, right, as a cosine t negative sine t, and then we get the unit tangent vector to be cosine t negative sine t. Does it make sense to have actually t to be in terms of, right, the tangent unit tangent vector to be in terms of parameter t? Wouldn't we need a concrete vector? Well, if you draw this, I practice drawing circles a lot, so you can see it's. I'm going to put it here. Wow. All right. Does this make sense? What I'm claiming is that this is the circle with the with the clockwise orientation, because r was given as sine t, cosine t, and we also have the unit tangent vector, which is given as I'm going to do that actually red. And I have the unit tangent vector in terms of t, which is given as cosine t, negative sine t. Does this make sense? Well, let's pick some t's. T equals 0. For t equals 0, I have vector r computed at 0 to be 0 and 1. Sine of t, right? Sine of t is, so sine of t is sine of 0, which is 0, and then cosine of 0 is 1. So we are starting here. And what happens next? What is the corresponding tangent vector? What is the tangent vector? 1, 0. Do we see that? Let's progress in time a little bit. Pi over 2. What's r of pi over 2? Meow? 1, 0. So we will hopefully agree that that's here. 1, 0. And what else? What's this guy? 0, negative 1.
That how you know the origin.
Ah, nice. You see, everything falls in place. Do you see how these tangent vectors are trying to spin this circle clockwise? Right? This one is pulling down, this one will be pulling this way, this one is pulling up. And when they all start pulling, this thing starts rotating, which is the motion over here, right? This is going to be back in chapter 14 for your vector fields. So you see the way all of this thing works. Now, obviously I give you a 2D, the cheapest possible thing that you can see. Now obviously you should go home and try something diabolical, right? See what happens with the helix. which way is helix going to work, right? It's going to go up. Well, we're going to do one now, but pick other. Slinky, right? You have that from the last class. There are many other options, guys, that you have to, and all you do is you just, play a little bit with it, and you will see which way the orientation is. It's all simple calculations. It's just time. You sit down, invest time to see what these things do. Let's take a look at a 3D case. We can do helix or we can do something else.
I'm kind of waiting for thinking. That may be late.
Yeah. Let's see. Unit tangent vectors. Oh, you're going to love this one. Here, problem 25. What is this equal to? For vector r given as t 2 over t. T larger than 0. No, t larger than 1. Let's see. Good. Let's take a look at this. We have r prime of t 1 0 and negative 2 over t squared. So now the magnitude of r, those of you having issues with derivative, you can think of this as t minus 1 like this, and then when you, right, comes negative 2, t to the negative 2. Right? Good. Calc 3. Now, we have magnitude, it's a square root, 1 squared plus 0 squared plus negative 2 over t squared, everything squared. This becomes 1 plus a square root of 1 plus 4 over t to the 4th. So what is our unit tangent vector? Is going to be vector 1 0 negative 2 over t squared divided by the square root of 1 plus 4 over t to the 4th. And now we just clear up some algebra and we're done. And before you ask me, do we have to? Yes. So this is 1 divided by square root of 1 plus 4 over t to the 4th. 0 stays 0. And you have negative 2 over t squared divided by the square root of 1 plus 4t to the 4th. Now when you rationalize, you multiply by the same square root, right? You have a square root of 1 plus 4 over t to the 4th up, and then you have 1 plus 4 over t to the 4 here. This one is still 0. And the second one is negative 2 over t squared times the square root of 1 plus 4 over t to the 4th divided by 1 plus 4 over t to the 4th. Now you have double fractions everywhere. You will multiply numerator and denominator by t to the 4th to eliminate double fraction. And that should give us good form. Principal unit normal vector is coming up. And in next week. And when that creature pops up, it's going to be derivative of this guy divided by the magnitude of itself. If you don't have it in simplified form, good luck. All right? So it's going to be some algebra grind at home to practice these things so they look good at least. So when the t to the 4th undergoes the square root, it becomes t to the 8th. So now this is a square root of t to the 8th plus 4, and then t to the 4, because t to the 8th divided by t to the 4 is t to the 4 in the numerator, and in the denominator you have t to the 4 plus 4. Now this one is still 0. Over here we can we cancel, right, a little bit. This and this cancels, leaves t squared behind. And you still have your negative 2. And now when t squared undergoes the square root, it becomes t to the fourth, and then plus 4. And down there is just t to the 4 plus 4. Are we happy with this?
Oh, spicy.
This is algebra. We're not done yet. One more. We can factor out t to the fourth, and it goes in front as t squared. And then t to the 4 plus 4 divided by t to the 4 plus 4. 0, negative 2, t to the 4 plus 4 over t to the 4 plus 4. Yay. There it is. Now that's much better form than what we had up there. If you are to go further with this for the unit normal, your principal unit normal vector later on, note that these are the same, right? If they are the same, you can actually just keep them as the square roots in denominator and then take derivatives. That's going to be much easier, right? So for later, algebra will give you t squared divided by the square root of t to the 4 plus 4, 0, negative 2 divided by square root of t to the 4 plus 4. So this is for later to keep taking derivatives. I believe this is 11.9 or 11.8, something like that. Next week, right? So next week, you are going to take t prime and divide it by the magnitude of t prime. And you clearly don't want any of the crazy expressions there, because you still have work to do with it. So more derivatives to come, right? But for now, we leave it at the red, right? You don't have any square roots in denominator. Everything is rationalized. Everyone's happy. And we move along. Is this hard? Hell no. You're just taking the derivative. The rest is algebra. It's tedious. That's all it is. And we have, let vector r of t be 1, 2t, 3t squared. Compute integral of r of t dt. Go. All right, so we are going to integrate term-wise. And each one of these now, the integral of r t dt is going to get its own constant, c1, c2, c3. So we have t plus c1, t squared plus c2, and t cubed plus c3. You can also write this as a vector t squared t cubed plus vector c, where the vector c is clearly c1, c2, c3. You can do that as well. All right, whatever makes you happy, because your happiness is our primary concern here at and the definite integral, just more of the same, just computed limits, all right? We can start. Good. Welcome. And I think, yep, that's it. I hope you're not disappointed. Now we have to do it again from scratch, so let's go back and redo everything. Say bye, right?